JMB, how are you all? I hope you all are good. I welcome you all to my YouTube channel. My name is Prince Ranpara. I am a PhD scholar in the Department of Chemical Engineering at the Indian Institute of Technology, Ropar. So in today's lecture, we are going to understand how we derive the design equation of the fluidized bed reactor by utilizing the concept of universal general mole balance equation, right? So let's get started. The first question which arises in our mind is, what is fluidized bed reactor? The second question which arises in our mind is, how the fluidized bed reactor differs from other industrial reactors. The third question which arises in our mind is, what are the significant applications of the fluidized bed reactor in the industries, right? What are the important assumptions of the fluidized bed reactor? What are the working principles of the fluidized bed reactor? Okay, so in today's lecture, we'll understand in very brief, because while understanding in the chapter number 5, where I will make you understand how we design the all the ideal reactors, right? So during the understanding in the of the chapter number 5, we'll delve more deeper into the fundamental understanding of the fluidized bed reactor. Okay, so in today's lecture we'll understand all the important concepts of the fluidized bed reactor in very brief. So let's get started. So first of all, we need to understand what the term fluidized bed reactor mean, right? So here this diagram represents the fluidized bed reactor. So fluidized bed reactor is a vessel in which solid catalyst particles are filled, through which the gas flows upward at the minimum fluidization velocity, where the solid catalyst particles are just suspended. The velocity is higher than the minimum fluidization velocity, where the catalyst bed becomes fluidized, right? Catalyst bed becomes fluidized. So in many operating conditions, right, in many operating regimes, right, so here the term operating regimes, which means a set of specific conditions or the operating parameters under which a system is functioning, under which a process is functioning, right? So in many operating regimes, the particle and the gas motions gives a very good mixing of the solid plus gas in the entire immersion phase of the fluidized bed reactor, right? And due to which the fluidized bed reactor, the immersion phase of the fluidized bed reactor will behave as a perfectly mixed reactor or continuously starting reactor, right? I hope up to here you have understood. Now let's say we'll understand the term fluidized bed reactor. Okay, so in order to understand the term fluidized bed reactor, we need to understand what the term minimum fluidization means. Okay, so let's say we'll understand what the term minimum fluidization. Okay, so let's say the minimum fluidization, which means or the minimum fluidization or the minimum fluidization velocity. Okay, the minimum fluidization velocity is the velocity of the flowing fluid through which the through which the through which the catalyst bed becomes suspended, right? The catalyst bed become expanded. Okay, it's called the minimum fluidization velocity. So at the minimum fluidization velocity, where the brake force of the flowing fluid will equalize to the weight of the catalyst bed. Okay, and that velocity is termed as the minimum fluidization velocity. Okay, so minimum fluidization velocity is a velocity of the flowing fluid at which the brake force of the flowing fluid will equalize to the weight of the catalyst, right? Will equalize to the weight of the catalyst. It's termed at that velocity, the catalyst bed will get just expanded. The catalyst bed will just get suspended. It's called the minimum fluidization velocity. So in minimum fluidization velocity, we also have three cases. The first case is, what if the velocity of the flowing fluid is below minimum fluidization velocity. The second case is, what if the velocity of the flowing fluid is equivalent to the minimum fluidization velocity. The third case is, what if the velocity of the flowing fluid is higher than the minimum fluidization velocity, right? So these are all the three cases important to understand. Okay, so let's say first case is where when the flowing fluid velocity is below the minimum fluidization velocity. So during those conditions, the solid catalyst bed will behave as a fixed bed, right? So there will be no expansion or suspension in the solid catalyst bed, which is present in the fluidized bed reactor, right? So here the solid catalyst bed or the emulsion phase or the dense phase is represented by the green circles, right? So when this gas when the fluid flows through the catalyst bed, there will be no expansion, there will be no suspension of the solid catalyst bed, and the solid catalyst bed will behave as a fixed bed, right? And due to which there will be linear increase in the pressure drop. Okay, so this was the first case. Okay, here we have completed the first case. Now in the second case, when the flow of the fluid when the velocity of the flowing fluid equalize to the minimum fluidization velocity, we'll understand that. Okay, so let's say in the second case, when the flow of the flowing fluid when the velocity of the flowing fluid equalize to the minimum fluidization velocity, so during those conditions, the drag force of the flowing fluid will equalize to the weight of the catalyst bed. Okay, so during those conditions, the solid catalyst bed will get just expanded, just get suspended, right? It's called the minimum fluidization velocities. Okay, and slightly higher velocities than the minimum fluidization velocity where the bed gets expanded. Okay, so where, okay, this was the third case. And when in the second case, this was the second case, right? And in the second case, when the drag force when the drag force of the flowing fluid equals to the weight of the solid catalyst, okay, the pressure will tends to remain constant. Okay, the pressure drop will remain constant, right? Okay, here we have completed the second case. In the third case, when the velocity of the fluid in the third case, when the velocity of the flowing fluid is higher than the minimum fluidization velocity. Now what will happen, right? When the velocity of the flowing fluid is higher than the minimum fluidization velocity, then the solid catalyst phase becomes fluidized, right? Solid catalyst phase become fluidized. So what does the term fluidized means, right? So fluidized means, so first in first case where we have the fixed bed of the solid catalyst, right? So fluidized means the solid catalyst bed will behave as a fluid, right? Fluidized, which means, let's say, like a boiling water, right? The entire emulsion phase or dense phase or solid catalyst phase will behave like a boiling water. It's called the fluidized, right? So the velocity is higher than the minimum fluidization velocity at which the solid catalyst bed or the emulsion phase will becomes fluidized, right? And during those conditions, the smaller bubbles will pass through the smaller bubbles will flow through the entire emulsion phase of the fluidized bed reactor, due to which we have the uniformly and thorough mixing in the entire emulsion phase of the fluidized bed reactor. Okay, I hope you understood. Okay, so I hope you have understood the term fluidized bed reactor and the minimum fluidization velocity and the three important case of the minimum fluidization velocity. Okay, now we'll well into understanding of the deriving of the fluidized bed reactor by using the general mole balance equation, right? So we already know the general mole balance equation is given by in minus out plus generation is equal to accumulation, right? So here the inlet stream is indicated by Fj0, which means the initial molar flow rates of species J entering in the fluidized bed reactor, minus Fj indicates the outer molar flow rates, right? Plus generation term Gj is equal to dnj by dt, right? dnj by dt. Now we are deriving the design equation of the fluidized bed reactor with respect to a reactant species A, right? So let's say here the inlet term is written as Fa0. Fa0 represents the initial molar flow rates of A entering into the fluidized bed reactor, right? Minus outlet term Fa, right? The final molar flow rates of A leaving from the outlet stream of the fluidized bed reactor, plus rate of generation of any chemical species in the reaction environment in the fluidized bed reactor, or the rate of disappearance of reactant species in the reaction environment during the progress of the reaction. During the progress of the time, the reactants will get consumed, will disappear from the reaction environment, and will get transformed into the new products, will be equalized to dNA by dt, right? dNA by dt represent the acclimation term. Okay, so in order to derive the design equation of the idealized fluidized bed reactor, we consider the steady state operation, right? So during the steady state operation, the acclimation term will be equalized to 0, which means there are no chemical species which are accumulating inside the reaction environment in the fluidized bed reactor, which means all the chemical species are exiting the fluidized bed reactor. Due to those conditions, due to the steady state operation, the acclimation term will be equalized to 0. Okay, so the Fa naught, so here we are writing the general mole balance equation as Fa naught minus Fa plus Raw is equal to 0, right? We are making the subject as Raw, and we are taking the Raw on the right hand side, so we need to consider the sign conventions, right? So we are making the subject as Raw, so therefore, and we are transferring the Raw to the right hand side. So here the positive sign will be converted into the negative sign. So minus Raw will be equal to Fa naught minus Fa. Now here we are making the subject as W. So W is equal to Fa naught minus Fa, and we are dividing this minus Ra on in the right hand side, right? So W is equal to Fa naught minus Fa upon minus Ra. Okay, so here we have derived the design equation of the fluidized bed reactor. So here the W indicates the weight of the catalyst which is required to reduce the initial molar flow rates of Fa naught to the final molar flow rates of Fa with respect to the rate of the reaction, right? So here this equation the equation represent the design equation of the fluidized bed reactor, right? So by using this equation, we can calculate the amount of catalyst which is required in order to achieve the desired conversion with respect to the rate of the reaction, right? I hope you have understood. Here we have completed the deriving of the design equation, right? Now let's say we'll understand some important assumptions of the fluidized bed reactor. Okay, so the first assumption is well mixed, the perfectly mixing in the dense phase, which means when the fluid flows through the entire catalyst bed of the reactor, we have the smaller bubbles we have the smaller bubble formation, due to which we'll have the uniformly and vigorously mixing of the entire emulsion phase in the fluidized bed reactor, due to which we'll have the thorough vigorously mixing of the entire gas solid phase in the fluidized bed reactor, due to which we'll achieve the perfectly mixed conditions, right? Perfectly mixing of the all the solid gas phase in the fluidized bed reactor, okay, which represent the perfectly mixed reactor or the continuous stirred tank reactor. Okay, the second assumption is the fluidized bed reactor is operated in the steady state conditions, right, where the acclimation term will be equalized to 0. The third assumption is reaction occurs on the catalyst surface. Okay, now let's say there will be the exchange of the gas which is present in the bubbles and into the dense phase is the solid catalyst phase. Okay, so the on the surface of the catalyst the reaction will takes place where we have the active sites presence, okay, on which the molecules get absorbed, reacted, and the products will get dissolved, right? So reactions occurs on the catalyst only. Okay, the fourth assumption is isothermal case, right? Gas and solids are in thermal equilibrium, which means let's say in certain reactions there will be the heat producing in the emulsion phase of the fluidized bed reactor. Okay, so we need to ensure the uniformly mixing of all the gas phase of all the gas bubbles and the solid catalyst phase in the entire emulsion in the entire reaction environment in the fluidized bed reactor in order to ensure the thermal equilibrium or the isothermal conditions, right? So we should not have any heat zones, right? We should not have any hot spots, right? Which means a certain position will have the higher temperature and other certain position will have the lower temperature. So we need to ensure then the temperature should be uniform throughout the entire position in position with respect to the length and volume of the fluidized bed reactor, right? So we need to ensure the thermal equilibrium of the gas and solid phase in the fluidized bed reactor. Okay, so we need to ensure the constant bed height. We need to ensure the constant bed height, okay, in the fluidized bed reactor, which means we should not have the higher or taller fluidized bed reactor with the higher height of the catalyst bed, right? So here from this position to this position represents the height of the catalyst bed, right? So we need to ensure a uniform optimized bed height in the fluidized bed reactor. Okay, the next assumption is uniform distribution of catalyst mass. Okay, so we need to ensure the uniform distribution of all the catalyst mass in the entire reaction environment in the fluidized bed reactor. There should be no bypassing, no channeling in the fluidized bed reactors, or there should be no dead zones presence in the fluidized bed reactor. So we need to ensure the uniformly distribution of all the solid catalysts in the reaction environment of the fluidized bed reactor. And we need to also ensure the flowing of the gas or the fluid through the fluidized bed reactor through the catalyst bed, right, in the upward direction should be uniform. Okay, the next assumption is the fluidized regime is stable, which means we need to operate the fluidized bed reactor in a certain operating regions, which means a specific set of conditions or operating parameters under which a system or under which a fluidized bed reactor is functioning, right? So we need to optimize the operating regimes of the fluidized bed reactor, and we need to ensure the stability and the steady state of operation of the fluidized bed reactor, right? Pressure drop across the bed is small or none. Last assumption is the pressure drop across the bed is small or none, which means when the velocity is higher than the minimum fluidization velocity, where the catalyst bed will become fluidized, right? So during those conditions, the pressure drop will get constant, or there will be a minimal pressure drop and the values will be known to us, right? So here we have understood the important assumptions of the fluidized bed reactor, right? Now here the one new question which arises in our mind is, let's say here I have explained that the fluidized bed reactor can be modeled as a CSTR, right? So this statement, how we model the fluidized bed reactor as a perfectly mixed reactor or continuously stirred tank reactor, right? We need to understand that. Okay, so this question which arises in our mind is, what does it means that fluidized bed reactor is modeled as a CSTR, right? So we understand. Okay, so the first point is high solid mixing, right? So we should have thorough vigorously mixing of entire solid catalyst bed in the fluidized bed reactor by ensuring the uniform gas uniform gas flow of the uniform gas flowing upward through the catalyst bed of the reactor. Okay, so we need to ensure the uniform distribution of the solid catalyst particle, the gaseous phase, and the uniformly mixing of the entire solid and the gas phase in the entire fluidized bed reactor, right? The motion of the gas and the solid particles will result in the uniformly mixing. Okay, we need the second point is the gas solid contacting is vigorously, right? Which means, okay, the gas solid contacting is vigorously. Okay, now what will happen? The gaseous phase which is present in the bubble will diffuses into the solid catalyst phase, right? So the gas phase which is present in the bubbles will get diffuses into the solid phase, right? They will get diffuses into the solid phase, right? So we need to ensure the uniformly and proper leaking or the diffusion of the gas from the bubbles to the solid catalyst, and we need to ensure we have the uniform and good solid gas contact, due to which the reaction will take place, and due to which the gaseous reactants will get adsorbed on the solid catalyst surface where we have the active sites present, right, where the reaction takes place, and where the reaction proceeds and reach to the completion of the reactions, right, and will get where the reactants get transformed into the new products, right. The third point is bubble burst and redistribute gases. Okay, now what will happen during the flow of the gases, during the flow of the fluid through the catalyst bed, where we have the smaller formation, where we have the smaller bubbles formation, right. So when the smaller bubbles flows through the entire length and height of the fluidized bed reactor, the smaller bubbles will collides with each other and will convert into the medium size of the bubbles, right. Now this medium size of the bubbles, when it moves upward to the catalyst bed of the fluidized bed in a catalyst bed which is present in the fluidized bed reactor in the okay, so when the medium size of bubble will move upward, the medium size of bubbles will collides with each other and will get converted into the bigger size of the bubbles, right, bigger size of the bubbles. Now when the bigger size of the bubbles will form, the bigger size of the bubble will burst, right, the bubbles will burst, right, the smaller bubbles will also burst, medium bubbles will also burst, and the bigger size of the bubbles will also burst in the emulsion phase of the fluidized bed reactor, due to which there will be a redistribution of all the gaseous phase which is present in the bubbles to the entire emulsion phase in the fluidized bed reactor, and due to which the gaseous and solid phase come in contact, they interact and the reaction takes place, and at the reaction comes to completion, right. The fourth point is the residence time of the solid is large, which means in the fluidized bed reactor we have the higher residence time of the solid as compared to the gaseous phase, right. So here we need to understand what does the term means residence time. So residence time, which means the amount of time which is spent by a molecule inside the reaction environment is called the residence time, right. How much time a molecule spends inside the reaction environment is called the residence time. Let's say, for example, if we have two molecules, okay, and one molecule spends 5 seconds in the reaction environment, the molecule will get react with this will get interact with the solid catalyst, react and get converted into the new product, right, and that molecule will remain in the reaction environment up to 5 seconds, and after 5 seconds the molecule will exit through the outlet stream of the fluidized bed reactor. So the residence time of that first molecule is 5 seconds, right. So now let's say the second molecules which spend 10 seconds in the fluidized bed reactor. Okay, so the residence time for the second molecule is 10 seconds, right. So residence time, which means the amount of time which is spent by a molecule in a reaction environment is called the residence time, right. So here the residence time of the solid is large, which means the solid will remain in the fluidized bed reactor in the form of expansion, right, in the form of fluidized bed reactor, in the form of fluidized, right, fluidized. Okay, so due to which the solid will have the higher residence times as compared to the gas, right. So so we can conclude here that the emulsion or the dense phase, the emulsion phase or the emulsion phase or the dense phase or the catalyst phase is very close to perfectly mixing, right. Perfectly mixing means due to the flow of the gaseous fluid, due to the higher velocities than the minimum fluidization velocity, all the solid catalyst particles will become fluidized, due to which due to the formation of the smaller bubbles will have the uniformly mixing and the distribution of all the solid gas in the fluidized bed reactor, right. We'll have the uniformly mixing in the entire emulsion phase of the fluidized bed reactor, due to which the fluidized bed reactor will behave as a perfectly mixed reactor. There will be a uniformly mixing in the axial direction as well as in the radial direction, right. So due to the uniformly mixing in the axial direction and the radial direction, will have the perfectly mixing conditions, right? Which means the fluidized bed reactor will behave as a perfectly mixed reactor, or fluidized bed reactor will behave as a continuously starting reactor, right? So these are all the points due to which we can say that this fluidized bed reactor can be modeled as continuously starting reactor or perfectly mixed reactor, right? Now, okay, I hope you understood. Now, one second question which arises in our mind is, now this statement, like the fluidized bed reactor can be modeled as CSTR or perfectly mixed reactor, is always valid. So we need to understand that, right? So let's say, what are the certain important points? By understanding and by considering those important points, where we can conclude that that the model, or the CSTR model, is not always true. Okay, in order to design, in order to model the fluidized bed reactor as a CSTR, right? So the next question which arises is, this is still only a model and not always valid, right? So what are the important points when CSTR model is not valid, where when the CSTR model fails, right, in order to model the fluidized bed reactor, right? So we'll understand those points, right? So first point is, when we will have very large gas bubble formation in the fluidized bed reactor, so which results in the slugging regimes, right? Slugging regimes, which means due to the formation of very large gaseous bubbles, okay, in the fluidized bed reactor, will have the slugging regime, right? So slugging which means due to the higher length and the height of the fluidized bed reactor, and the uh, narrower diameters of the fluidized bed reactor, due to which the smaller bubbles will get converted into the larger bubbles, right? And the larger bubbles of equivalent inner diameter of the fluidized bed reactor, okay, due to which there will be a separation, due to which the solid catalyst particles will behave as a some plug or slug, right? So let's say here we have the formation of the very large bubbles, right, of the equivalent to the inner diameter of the fluidized bed reactor. So where we'll have the suppression of the solid catalyst particle in the upward side as well as in the below side, okay, due to which, due to the formation of this slug, right, due to the formation of this slug, will not have a uniformly mixing of the solid gas in the immersion phase of the fluidized bed reactor, okay, so which result in the slugging regimes, right? So slugging regimes, which means certain specific set of conditions or the operating parameters under which a fluidized bed reactor will behave as a slugging regimes, right? As a slugging, which means the formation of a very large bubble which separates the catalyst bed, okay, in the upward side as well as the below side, right? So okay, it's called the slugging regime. Okay, so during these conditions, the fluidized bed reactor cannot cannot be modeled as a CSTR. Okay, so here the CSTR model fails. Okay, the second point is strong axial gradient or poor mixing. Okay, now due to the formation of the large bubbles, okay, in the fluidized bed reactor in the emulsion phase in the reaction environment, due to the formation of very large bubbles, due to the formation of the slug, will have a poor mixing or will have this strong gradient in the axial direction, right? So here these direction represent the axial direction, right? Axial direction. So we'll have a strong gradient in the axial direction, and okay, axial direction, right? So gradient of what? So gradient of all the reaction parameters, right? So let's say we'll have, due to the slugging regimes, okay, we'll have the strong axial directions, axial gradient. So the reaction rate will vary through the axial reaction, the concentration, temperature, pressure, rate of the reaction, rate of the generation will vary through the entire length, volume, and axial direction of the fluidized bed reactor and will result into the poor mixing of the solid and the gas phase in the emulsion phase of the fluidized bed reactor. Okay, so during those conditions, the CSTR model fails. Okay, so in order to model the fluidized bed reactor is a CSTR. During this condition, the CSTR model fails. Okay, the third point is very fast reactions, the rate controlled by external or internal diffusion. Okay, so let's say, so we'll understand that point. So let's say now what will happen. Now these bubbles will have the bubbles in which the gaseous phase is present. Okay, now this gaseous phase will interact with the solid catalyst, right? Now what will happen. Now from this gaseous phase, let's say what will happen. Now from this gaseous phase, the gas which is present in the bubbles will diffuse or leak will leak into the emulsion phase, right, on the solid catalyst. So where the due to the diffusion, internal diffusion and the external diffusion of the gaseous phase on the solid catalyst surface will result into a very fast reaction or variation in the rates of the reactions. Okay, due to the limitations of the internal diffusion or the limitation in the external diffusion, which results into a very fast reactions or there are no reactions, right? So during those conditions, the CSTR model fails, right? So we cannot model the fluidized bed reactor as a continuously starting reactor because we need to have perfectly uniformly distribution of all the gaseous phase with the solid phase. Okay, throughout the entire reaction environment in the fluidized bed reactor. Okay, so we need to have uniformly distribution of each and every reaction parameter with respect to the each and every position in time, right? Which means we need to ensure uniform distribution of rate of the reaction, concentration, temperature, pressure throughout the entire reaction environment in the fluidized bed reactor. Then only we can say the fluidized bed reactor can be modeled as a CSTR. Otherwise, the CSTR model fails. Okay. The fourth point is poor bubble emulsion mass transfer. Okay. So the fourth point is poor bubble emulsion mass transfer. Okay. So same way I already explained. So bubble is, so here we have the bubbles, right? So in the bubbles we have the presence of the gas phase and the gas leaks into the emulsion phase. Emulsion phase is the solid catalyst phase or the dense phase, right? So gas leaks from the bubbles to this emulsion phase, but we have the poor mass transfer, poor diffusion of the gas phase into the emulsion phase, due to which this CSTR model fails, and we cannot model the fluidized bed reactor as a CSTR. Okay, I hope you have understood, right? Now let's say the fifth point is very tall reactors. Let's say what if the length of the reactor is very tall, is very high, length of the reactor is very large, okay, and the bed of the catalyst is very large. Now what will happen? So during those conditions we'll have a certain distribution of the behavior of the in the fluidized bed reactor. Let's say the solid will behave as a continuously starting reactor and the gaseous phase will behave as a PFR. So during these condition of very tall reactors, when we'll have very tall reactors, we'll have the distribution of the solid as a continuously starting reactor. The solid phase will behave as a continuously starting reactor and the gas phase will behave as a PFR, which means we'll not have uniform CSTR. We'll have the mixture of the PFR and the CSTR. So due to those reasons, during these conditions, we cannot model the fluidized bed reactor as a CSTR. Okay, I hope you have understood. So let's say what will happen. Let's say if we are having a very tall reactors, now what will happen? The small gas bubble will get released. The small gas bubbles will move upwards in the solid catalyst phase, and will the uniformly mixing of the solid and the gas phase takes place, due to which the small bubbles will collide with each other and will form a big bubble equivalent to the inner diameter of the fluidized bed reactor. Okay, so what will happen now? This here in this part, the solid catalyst in this part, the solid catalyst phase will behave as a continuously starting reactor. So because here in this part we have the smaller bubbles, right? Due to the presence of the smaller bubbles and the vigorously and thorough mixing with the solid phase will have the uniformly mixing. So the solid phase or the emulsion phase will behave as a CSTR, and the gaseous phase will behave as a PFR, right? So due to those reasons, the we cannot model the fluidized bed reactor as a CSTR. Okay, so during those conditions, the CSTR model fails. The sixth point is non-uniform particle size or poor fluidization quality, which means we should have uniformly distribution of all these solid catalyst particles in the fluidized bed reactor, right? If we are not ensuring the uniform distribution of all the solid catalyst particles, and if there are presence of the channeling or the bypassing or the dead zones or the agglomerization of the solid catalyst particles, will result in the non-uniform particle size distribution throughout the entire fluidized bed reactor in the emulsion phase of the fluidized bed reactor. Okay, due to which the fluidization quality will reduce. So and will not have uniformly mixing of the gas solid phase present in the emulsion phase of the fluidized bed reactor. So during those conditions, we cannot model the fluidized bed reactor as a continuously starting reactor. So due to this condition, the CSTR model fails, right? So I hope you understood when we can apply, what are the important conditions, what are the important conditions when we can apply when we can model the fluidized bed reactor as a CSTR, right? What are the important conditions when we can model the fluidized bed reactor as a continuously starting reactor or perfectly mixed reactor, and what are the important conditions when we cannot design the fluidized bed reactor, we cannot model the fluidized bed reactor as a continuously starting reactor. So these are all the important conditions, right? I hope you have understood. So let's say, in order to summarize the entire lecture, so here is the summary of the entire today's lecture. Let's say, what if we are having what if the fluidized bed reactor, we can model the fluidized bed reactor as a CSTR model, right? So when we are having the CSTR model, when it is valid, okay, when it is valid, which means we can model the fluidized bed reactor as a CSTR. So what are all the important points is we should have the good particle mixing. Second important, we should have the good particle mixing. Second is bubbles not too large, right? We should have smaller formation of the bubbles, due to which we'll have uniformly and vigorously thorough mixing of the entire solid in the gas phase in the emulsion phase of the fluidized bed reactor. The gas exchange between the bubbles and the emulsion is strong, right? Which means the gas present in the bubbles should diffuses or leak to the emulsion phase should be very high, right? So when the gas diffuses or leak from the bubbles to the emulsion phase into the emulsion phase is very high, then we'll have a good rate of the reactions, right? Good exchange of the gas and solid phase, and the reaction takes place, and the conversion of the reactants into the product takes place, right? And which also depends on the speed of the reactions, right? Bed height not very large, right? So we should not have very tall reactors. Okay, now we need to avoid the slugging and channeling regimes, right? I already explained what are the slugging regimes and slugging regimes, right? So we need to avoid all the slugging regimes, right? The superficial velocity is good. The superficial velocity in good fluidization range. Okay, now here the superficial velocity, which means the imaginary, right? Which means, let's say, in order to understand the superficial velocity, we'll understand that, let's say, in the fluidized bed reactor, where we have the presence of solid catalyst, right? In order to understand the superficial velocity, we need to assume that there are no solid catalysts present in the fluidized bed reactor. Okay, but in reality the solid catalysts are present. Okay, but when understanding the superficial velocity, we need to assume that there is no solid catalyst present in the fluidized bed reactor, and gas is flowing with the velocity. So that velocity by which the gas flows through the empty fluidized bed reactor is called the superficial velocity, right? So superficial velocity plays a very important role in order to understand, in order to design and compare the fluidized bed reactor, right? In order to design the fluidized bed reactor. Okay, so when these when these all conditions are satisfied, okay, when all these conditions are satisfied, we can design the fluidized bed reactor. We can model the fluidized bed reactor as a continuously starting reactor, right? So CSTR design equation is reliable here. Okay, so we can design the fluidized bed reactor as a continuously starting reactor or perfectly mixed reactor. Okay, so fluidized bed reactor is model as a CSTR. Okay. Now, in contradictory to these, we have when the CSTR model is not valid. Okay, when we cannot model the fluidized bed reactor as a continuously starting reactor. So, first condition is when we have the formation of very large bubbles and the slugging regimes, due to which the CSTR model fails. Okay, when we have the long bed height and the axial gradients, right? The presence of the axial gradient and the tall reactors and the long bed height, due to which we cannot model the fluidized bed reactor as a CSTR. When there are fast reactions, we have the limitations of the internal diffusion and the external diffusion in the emulsion phase in the fluidized bed reactor in the reaction environment, due to which we cannot model the fluidized bed reactor as a continuous stirred tank reactor. The poor phase exchange, which means the gaseous phase present in the bubbles and the solid phase present in the emulsion phase, right? It's all the So when there is a poor exchange between the gas and the solid phase in the reaction environment of the fluidized bed reactor, so due to which there will be a non-uniform mixing of the solid gas phase present in the reaction environment, due to which the CSTR model fails. Okay, the poor fluidization quality, right? Due to the poor fluidization quality, due to the poor fluidization regimes, the we cannot model the fluidized bed reactor as a continuously starting reactor. The broad particle size distribution, right? The operating, and when we operate the fluidized bed with a lower velocities than the minimum fluidization velocity, right? When the fluid flow with the velocity lower than the minimum fluidization velocity, where the catalyst bed will remain fixed in stationary phase, due to which there will be no expansion, no suspension of the catalyst bed, due to which there will be a linear increase in the pressure drop. Okay, so during those velocities, we cannot model the fluidized bed reactor as a continuously starting reactor. So these are all the conditions due to which we cannot model the fluidized bed reactor as a continuously starting reactor. I hope you have understood, right? So in order to conclude this lecture, we have understand what is fluidized bed reactor, how the fluidized bed reactor differs from other industrial reactors, what are the significant importance of the fluidized bed reactor, what are the important assumptions of the fluidized bed reactor, what are the working principle of the fluidized bed reactor, right? Followed by understanding and deriving of the design equation of the fluidized bed reactor by considering by modeling the fluidized bed reactor as a continuously starting reactor or perfectly mixed reactor, and by understanding all the important concepts and the conditions at which we can model during which we can model the fluidized bed reactor as a CSTR, and all the important conditions during which we cannot model the fluidized bed reactor as a continuously starting reactor. I hope you have understood. Okay, so if you have any questions, if you have any queries, then feel free to comment below. I will try my best to reply to your comments. Okay, so in the next upcoming lectures, we are going to solve a numerical example of all the idealized reactors, right? Okay, and if you want me to make a special video on designing of on deriving the design equation of the semi-batch reactor and the bioreactors, please comment below. Okay, and I will try my best to make a special video on deriving the design equation of the batch reactors, semi-batch reactors, and the bioreactors. Okay, so and I request you to please make all the notes, right? And if you have any query, feel free to comment below. I try my best to reply to your comments. Okay, so thank you for watching my video. I request you to please like this video, please share this video with your friends, and please subscribe to my YouTube channel. Thank you for watching my video. Jai Ambe.